All right, welcome back for the second video for lecture 3 for week 9. We are looking at the kinetic theory of gases. So in the first video, we figured out what the root mean square velocity of a sample of gases, gas particles, is based on the temperature. And we just basically verified that idea that temperature is kinetic energy. So we saw that the average kinetic energy is 3/2 times K times temperature, K being Boltzmann's constant. And we're now going to look at the distribution of speeds in an ideal gas. We said that the speeds, the particles in a gas aren't all the same speed. They aren't all driving around at exactly the same speed. They are a variety of different speeds. They have a variety of different speeds. And we're going to start talking about what that distribution actually looks like, what the number of particles with each different speed might be. So we'll go here. So the reminder on the previous slide was just that we are now talking about speeds, not velocities. Each particle in an ideal gas has a random velocity. The root mean square of these velocities tells us about the kinetic energy, which relates to the temperature of the gas. So that's just restating everything we saw in the first video. So what does the distribution of the speeds of the gas particles look like? Right, so they're not all the same. We're going to have some particles with more energy, some with less, which means some with higher velocity and some with lower velocity. But how many at each different velocity? What do we actually have? What does this look like? James Clerk Maxwell is the guy that figured out what it actually looks like. He came up with this equation, and so in accordance with him being the discoverer of it, it is called the Maxwell distribution of speeds. Now that is a messy equation. You don't need to remember it, you don't need to prove it, you don't need to even necessarily understand where it comes from. All you need to do is to be able to understand what it tells us. Right? We need to be able to interpret this equation. Now, it is messy, but let's just have a look at it for a moment and see what it's got in it. So there's a couple of pi's in here, some numbers. Those sorts of things don't matter too much. They're just constants that obviously make the equation come out correctly. But with the actual terms we've got, the number of particles, big N here. We've got a mass, so the mass of the particles. So this is assuming every particle in the gas has the same mass, which is what happens when we take an ideal gas of everything being the same. We've got Boltzmann's constant K, M and K both in both of these terms. Temperature is in both of these terms. And we've got the velocity here and here. So what this equation is doing is it's saying you put in the properties of your gas, how many molecules, the mass of each molecule or particle, not necessarily molecules, the mass of each particle, put in these constants, obviously they're all just Van numbers, put in the temperature of your system, and then what you do is you go through and for every possible velocity, you calculate this function, right? So that's what functions are. We often see y as some function of x. This is just saying f of v, some function of v, of the velocity. So as the velocity changes, the value that we get out of this equation will change. But we'll talk about interpreting it in a moment. But at the moment, as long as you can see what all the terms are, there's nothing overly surprising or complicated here. This is an exponential, right? E to the power of all of this. Just in case that's not clear from the size of that bracket, it's very big, exponential of all of that. So that is the Maxwell distribution of speeds. You need to be able to do that, but there's nothing, no complicated maths there, just a big equation. And it looks something like this. The exact shape will vary depending on the properties of the system, but it'll always look something like this. A couple of points to note that when you get down to 0 on your velocity axis, so get down to 0 on your velocity axis, obviously you'll have to be at 0 on f of v because you can't have any particles below 0, right? There'll be no particles with energy less than 0, and actually right at 0 it will be 0. Right? You can't actually have any that have exactly 0 velocity. They'll always have to be moving with some finite velocity, even if it's tiny. And then as you increase velocity, you get more and more particles with that velocity, more and more, all the way up to some peak velocity. That's the peak, the most probable velocity. And then the actual average velocity is higher than the peak velocity. And that's because this is not symmetrical. right? So this is not a symmetrical curve, and it's not symmetrical because it's forced to stop at 0 here, but this peak can, this tail on this side can go out really far, right? It can go quite far. There's nothing stopping it. You can get faster and faster particles. The overall temperature and energy of your system will determine how many there are at those higher velocities, higher kinetic energies. But you can still get them up here, whereas you can't get them below 0. So it means we're not symmetrical, which means that those higher velocity ones where you can't get negatives are going to skew this curve, and we get an average which is actually higher than the peak. And just for reference to the previous values we saw with VRMS, the VRMS value, the root mean square velocity, is higher still than the average. So we have peak is at the peak of our graph, and that's the most probable, most likely velocity of any particle. This is the average velocity of all the particles, and this is the root mean square velocity of all the particles. So they're all a bit different, and they all have different meanings and different uses. But you need to recognize this shape. So how do we interpret it? Right, well, it turns out that, well, not turns out, it was designed so that the area under the distribution tells us the number of particles that will be in that range of velocities. So you don't just go and calculate f of v at some point and say, oh, there's that many particles with that velocity. That's not how it works. You need to get an area, right? So you need to get an area of velocities on the graph. Choose 2 velocities, and then the area under the graph between those 2 velocities. That tells you the number of particles with a velocity in that range. Right. So yeah, if you want to do V1 and V2, you just draw in this shape. You fill in this. So this is just a segment of the graph. You can see it's part of this bit of the graph over here. And you just draw in this, figure out this area here, and that will be the number of particles with velocity between V1 and V2. So if we set V1 to 0 and V2 to infinity, that means we're going from here to infinite velocity, and we want the area under the graph. The area under the graph must be big N, must be the number of particles, because the number of particles with a speed between 0 and infinity must be all of them, and all of them is N. So the area under the graph is actually big N. A little simplification that makes our job a lot easier is that for most of the area on the graph, assuming you're not using really big ranges, you can actually find the area, or very close approximation to it, by finding the function in the middle of that velocity range, and then multiplying it by the width of that velocity range. Right? So you can see if you find the height in the middle here, and then make it a rectangle, so multiply by the width, that's an area, right? A length times a width, that's a rectangular area. That is pretty much the same as it was before, because this little bit where we've cut out, we've added on a very similar bit on this side. So as long as our velocity range isn't too big, then this approximation works very well. We can just find one function, one value of the function, and get an area that way, rather than having to go and calculate a whole bunch of different ones and figure out the shape of the curve. And it gets very complicated. It gets into integrals is the way that we would solve it for for bigger areas, but you don't have to worry about that. All you have to worry about is that for a small velocity range, find the height times by the area, which is the distance between those 2 velocities. Right, so that's how we get to the number of particles. That area, remember, is a number of particles. So what happens to this distribution as we change some of the properties of our system? Since the distribution is telling us about the velocity, but we know temperature relates to kinetic energy has mass and velocity in it. So if we have a heavier particle, it should have less velocity, right? Because half mv squared, if m's going up, but we're keeping the kinetic energy the same, then that means that the velocity can go down, or will go down. And that's indeed what we see. We've got 2 curves here. Everything about the system is the same except for the mass, where the mass of the blue particle is half of the mass of the green one. Right? So if the blue particle has half the mass, then the velocities have to get higher. So you can see that it changes the shape of the curve. Our peak is from here, is now over here. And it also means that the higher up velocities, we get a lot more of these higher velocities than we did there. So that's just changing the shape, and again, shouldn't be any surprise given temperature is kinetic energy. If we change the mass, the velocities must change as well. What about if we change the temperature? Again, if we're increasing temperature, we're increasing kinetic energy. If we're increasing kinetic energy and the masses are staying the same, then we must be increasing the velocity. So what we've got here is some distribution at some temperature T, and then the green is the same particle, same system, but now with a temperature 100 Kelvin higher, right, or 100 degrees Celsius higher. It's an interval, doesn't matter which units we're using. So in a temperature 100 Kelvin higher, we now have a slightly higher peak, right? The average kinetic energy is going up, which means the average velocity must go up. So that's what happens when we change aspects of the system. Shouldn't be any surprise given our understanding of temperature, kinetic energy, and so on. Just to cross over for a moment to chemistry, for those of you that have studied any chemistry at all, you will have met something called activation energy, and it's the amount of energy required for some chemical reactions to occur. And it's the amount of kinetic energy that the particles need to have so that when they collide with another particle, rather than just having a nice elastic collision, they actually penetrate into each other a bit, they overlap a bit, and then they can actually chemically react with each other, and the reaction occurs. So basically what we're saying is that the activation energy is how much energy you need for an inelastic collision to occur that results in that chemical reaction. It's pretty well known that those sorts of reactions occur more rapidly as temperature increases, and this Maxwell's distribution shows us that that makes perfect sense. Because if we choose some activation energy and figure out the velocity needed to get that activation energy, right, then you can see that at that point, the higher end temperature, the green one, the higher temperature has a lot more area here, right? So a lot more particles than the blue one does. The blue one's only got this area, and then the green one's got this whole area here. So we get this, we get the far more particles with enough energy to cause the chemical reaction to occur. So it makes perfect sense that these slightly higher temperatures, even just a small change in temperature for the overall temperature of the system, can cause a big increase in the number of particles that get over that activation energy. All right, so that's all we're going to say about Maxwell's distribution. As I said, you need to be able to apply it. There is a question relating to applying Maxwell's distribution and making sure we understand that fully. But let's just take a moment and talk about other types of energy. Temperature was a measure of translational kinetic energy. So translational just means that it's translating from one point to another point. So translation is a mathematical term. It means just without changing anything else, you just move it from one place to another. So that's what translational kinetic energy is referring to. If that's what temperature is, then what other kinds of energy can a particle actually have? Right. There's a bunch. One example is vibrational energy. So if you've got a particle that is actually a molecule, for example, O2, the two atoms could vibrate back and forth. Just like if you've got two masses on the end of a spring and set them oscillating, they're going to vibrate back and forth. The same thing can happen here with the atoms and the chemical bond is acting like a little spring in the middle. So this kind of energy is actually oscillating between kinetic and potential energy, just as we saw with SHM. So it would have kinetic energy when the particles are moving away or towards each other. And then it's got potential energy, which is like our spring potential energy, but in terms of the bond being the spring. And that's going to be potential energy when you're at their maximum or minimum position relative to each other. So it will oscillate between kinetic and potential energy, but we can call it the whole package vibrational energy. So if they get some vibrational energy, so they're oscillating with each other, then that means that there is some other kind of energy there. So now this molecule, it can still have translational energy. The whole molecule might be moving, but as it's moving, it's oscillating in and out with each other. And so we've got this other kind of energy. The temperature is still just talking about the translational one, but we're saying it can have this other form of energy. Also, it could be rotating. So as it's translating along, it's still translating. It's always got that, there's always got some translational motion, some translational kinetic energy, but it might have rotational kinetic energy as well. So as it's traveling along through space, it's rotating around its center of mass. So that would be just rotational kinetic energy. So we have other forms of energy. And all of these different types of energy, the rotational, the vibrational, the translational, whatever other kinds you can think of, whatever other kinds there are, if you add all of them up for each particle and get the total energy of that particle, and then add all the energies of all the particles in your system together, you get what we call the internal energy of that system, of that substance. Okay? So for internal energy of a gas, you'd have to watch every little possible gas molecule. You'd have to measure its rotational energy, its vibrational energy, its chemical potential energy, all the other, whatever kinds of energy it might have, and the translational kinetic energy, obviously. Add all of those together to find the total energy for that gas particle. Do that for every one of all your gas particles. Add all of those total energies up, and that gives you the internal energy. So the internal energy is all of that energy in the system. Sometimes people call it thermal energy. I prefer not to do that. It's not incorrect, but I prefer not to do that because it makes it more confusing when we're saying that temperature is only translational kinetic energy, to then call all of the internal energy thermal energy. It's unnecessarily confusing. So I tend not to do that, but it's worth being aware of because sometimes you will see that in problems or questions. There are, as I said, there are other kinds of internal energy. We're not going to go into them. You just need to be aware that they exist. And as I was just saying, just to be really clear about this, temperature is the measure of the average translational kinetic energy. Right? Remember that it's average kinetic energy was given by 3/2 kT. So temperature is just relating to that translational kinetic energy. The internal energy is the total energy of all the particles in a substance. And heat, which we haven't met yet, but we will come back to in another lecture, is the transfer of internal energy between two objects due to a temperature difference. So we are going to come back to heat and energy transfer I think it's next week. I've written next week, hopefully it is, but we will come back to that. The last thing that we want to just mention is we've been talking about ideal gases. Now we've introduced this concept of internal energy. What does the internal energy of an ideal gas look like? Well, we said when we made our assumptions for the ideal gas model, we said that these gas particles are essentially just hard little spheres, and so they're not going to be rotating, they're not going to be vibrating, they're not going to be doing anything else. They're single spheres, so they're not chemically bonded with anything else. We have essentially no other way that it can store energy, right? It can't do the vibrating, the rotating, the chemical bonding or anything else. So that means that all it can have is its translational kinetic energy. So that means that the internal energy of an ideal gas actually is just the translational kinetic energy, which is just the number of particles times the kinetic energy of each particle. Right? And so if we take our average kinetic energy, which we know is 3/2 kT, we can just multiply that by N. So we find that the internal energy of an ideal gas is 3/2 NKT. So that's the content for topic 3. As usual, there's a little review slide there. Just read through that, make sure you're happy with all of those. Anything you want, go back and double check. There will be another short video coming up for some questions. I think I've got 3 questions relating to this content. So keep an eye out for that video, but that is the content for topic 3 and therefore the end of the content for week 9.